Dear GATE aspirants, once again, I welcome you on behalf of Easy Gate to GATE 22 Electronics and Communication Paper Memory Based Questions and Solutions. Okay, once again, I stress on the paper. The paper is easy relatively comparing to the GATE 22 paper. So you will feel that while going through the problems. Okay, so already I'm solving the problems based on analog circuits or analog electronics. So I'll be getting into the next problem. This is from NMOS. Okay, so it's memory based. The data may not exactly match with the given paper. I'm trying to get that number very closer to what is given in the actual paper. Okay, anyway, you will come to know exactly the question maybe in another 5 days. Okay, once response sheets are out, okay, you will come to know, and we'll try to fine tune that. Once again, we'll upload you a video with the proper question. Okay, yes. Till then, the structure of the problem is not changed. Maybe the data small change, okay, might have happened in the data taken because it is purely memory based. Okay, yes. So that's a problem. Okay, given with NMOS. Okay, and hopefully the data given are almost closer to the paper. Fine tune this data. So given NMOS, no problem figure is given. Given an NMOS, okay, N channel EMOSFET, its gate voltage or its gate is excited by 2 minus sine omega t volts. Omega may be given, but I didn't remember that exactly. So I'm going with 2 minus sine omega t volts. That's a excitation to the gate. That means you need to imagine immediately an NMOS having 3 terminals. This is the gate. This is your channel between drain and source. That's an analog circuit symbol of an NMOS. What is given is the gate is excited by 2 minus sine omega t. So the gate voltage is given. Okay. So probably instead of a gate voltage, it may be a gate to source voltage. Okay. So that gate to source voltage means you can take the source as a reference. Okay. Ground. So 2 minus sine omega t exciting the gate. Okay. That means the entire voltage is going to serve as a VGS. Let me write it here. So whatever the voltage applied to the gate to source will be appeared across this. That's your VGS. So what is given as VGS of t, that is equal to 2 minus sine omega t. Okay. So this has two components. One is the DC component, another one is the AC component. So a DC plus AC is applied, okay, to the gate to source of your NMOS. And also given the width to length ratio of the channel is given as 10 indirectly, and mu and Cox is given, the product is given as 1 milliamps per whole square. So with that, one can calculate straight away the Kn, that is half of mu n Cox into W by L. So the result is going to be Kn will be equal to, yes, it's going to be half of W by L will become 5. So 5 into 1 milliamps per whole square. So the device constant is going to be 5 milliamps per whole square. Usually we look for two data. One is threshold voltage, another one is Kn. With that, we can pick a straight away. We'll play with either ohmic state of operation of NMOS or saturation state of operation of NMOS, because the VGS is going to keep the device in on condition, assuming, okay, if the device is on, if NMOS is on, it may be either in ohmic or it may be in or in saturation. Okay, fine. So the threshold voltage is given as 1 volt. So therefore, with respect to the NMOS characteristics, you have to imagine quickly the NMOS characteristics. This is ID versus VGS saturation characteristics. So this is your threshold voltage given. Okay. So any VGS more than 1 volt will keep the device in on condition. So it has to obey the condition for saturation or ohmic. So VDS is greater than VDS pinch off, then the device is in saturation. Suppose if VDS is going to be less than VDS pinch off, device is going to be in ohmic. What is VDS pinch off? Hope you remember. The VDS pinch off is nothing but the gate to source voltage minus the threshold of your NMOS. Okay, that's for your NMOS. So this is the data. So we know how to play with this. Then extra data is given, the voltage between drain to source is given as 1 volt. This voltage is given as 1 volt. Yes. So if that is the case, I will take the drain potential as 1 volt. So it's a constant. VDS is a constant 1 volt. It is not having any variation. Only VGS has a sinusoidal variation. So problem is the maximum drain to current, drain to source current, or shortly the drain current of the NMOS is. What is the maximum current in the channel? That is the problem. So how to proceed for this problem? We'll see. So first, let us draw the VGS of T waveform. VGS of T waveform will be this. What is the given VGS of T? It is 2 minus sine omega T. So what is the DC level? 2 volt. So with respect to the 2 volt DC level, it is down because 2 minus. So initially it is down. So it is going to be this way, 2 minus. Okay, 1. It is going to be my 1. And then it will go to the first sine omega t positive of cycle means result is going to be the negative because it's minus sine omega t. It is equivalent to 2 plus minus sine omega t. So I am adding minus sine omega t with the 2. Minus sine omega t will begin with straight away negative of cycle only. So this is the waveform for a cycle. One cycle, let me take. So this is one cycle waveform. Okay, so problem is maximum drain to source current. Okay, that is your channel current. So how to get the maximum? Maximum is possible when VGS is maximum. Okay, so when VGS is maximum, probably the channel current will be maximum. So let us find the maximum voltage. So what is the maximum voltage? So this is the maximum voltage. What is this swing? It's 1 volt. What is the swing? It's also 1 volt. So what is the maximum then? It's swinging by 1 volt from 2 means this maximum will be what? 3 volt, and minimum will be what? 1 volt. Okay, so therefore VGS maximum is 3, minimum is 1, and its DC level is 2 volt. That's what given. So therefore I may feel that ID max can happen only when VGS is maximum. So let us set the problem at VGS max, that is equal to 3 volt. Okay, so let us set the problem here. So NMOS this voltage is given 1 volt, and this is now taken as 3 volt. I'm taking VGS equal to 3 volts. So VGS equal to 3 means, yes, you know, device is definitely in on condition. Okay, so this is 3 volt. That's what it means. So gate is at 3 volt, drain is at 1 volt. So VDS is equal to what? 1 volt. That's what he said. That's a given data. Let us find VDS pinch off for the given data. So VDS pinch off is equal to the given VGS minus V threshold. Problem is to find the maximum current. So I am setting the problem at maximum gate to source voltage. Okay, that is logical. Okay, now let me check whether the given device, when the gate potential is equal to 3 volt or when VGS equal to 3 volt, whether it is in saturation or ohmic. So for that, let me find VDS pinch off. What is the VDS pinch off? VGS equal to given 3 volt minus V threshold is given. What is the V threshold of the NMOS? 1 volt is given. So the VDS pinch off is equal to 1 volt. Okay, usually we assume the device is in saturation, so we go for the saturation current. So if you go for the saturation current, then ID will be equal to Kn already determined into VGS minus V threshold of NMOS the whole square. Okay, so if you go by that, so for this ID is equal to, you'll get 5 milliamps per whole square. That's already known, and VGS now is equal to 3 minus 1 the whole square. So as a result, you will end up with a current of, so it is 3 minus 1 whole square is going to be 4 whole square. So, okay, yes, 2 volt whole square, 4 volt square into 5 milliamps per whole square will result in a current of 20 milliamps. And this is subjected to a verification. VDS should be greater than what? VDS pinch off, because that is the one spelling what? Saturation. Okay, that's a necessary condition to prove that NMOS in saturation. But now what is happening? We have to check it, okay, whether it is in saturation or not. Given VDS equal to 1 volt, and now we have determined the VDS pinch off equal to what? 2 volt. Therefore, We are looking to prove this can be the answer. If VDS is greater than VDS pinch off, device is said to be in saturation. We can happily give the current as 20 milliamps. Probably one of the options given in the problem is 20 milliamps. I didn't remember that exactly. Then let me go for that VDS pinch off. So VDS pinch off is equal to 2 volt. Therefore, it is confirming your VDS is less than VDS pinch off. So device is not operating in saturation. Therefore, current cannot be 20 milliamps. So therefore, exploiting the saturation equation is invalid. I can't use this for this problem. Okay. So problem again. Yes, you are getting into the real problem now. So device is actually in what? Ohmic. So device is in ohmic. The given NMOS is operating in ohmic state of operation. Then you have to remember only two equations, ID for saturation, ID for ohmic. Then what is ID for ohmic? ID for ohmic is equal to what? Kn into, it's also very easy to remember, 2 times VGS minus V threshold of your NMOS into the VDS minus V square DS. So device is not in saturation. So if you remember the characteristics, this is VDS and this is your ID. Roughly, this is ohmic and this is saturation. This is the pinch off point. What is the pinch off voltage? For the given VGS. Given VGS equal to how much? 3 volt. Okay, that means I'm playing for the maximum. So assuming VGS equal to 3. So then the VDS pinch off is equal to 2 volt. VDS pinch off is equal to 2 volt. So this current we have determined, assuming if it is in saturation, this is 20 milliamps. It is unfortunately not in saturation because VDS is less than 2. Okay, but don't go by linear interpolation. This is the rough curve. Okay, so 1 volt. So 2 volt 20 means 1 will be 10. No, don't do that. Okay, we'll go for the exact analysis. So it is found that device is operating strictly in ohmic, not in saturation. Therefore, we are free to use the ohmic equation. So no guidance given by the designer because he never told us devices in saturation. So it's up to us to find out whether the given conditions, voltage given to VGS, voltage given to VDS, keeping the device in ohmic or saturation at the maximum point, then play accordingly. Okay, now we found that device is operating in ohmic. Therefore, we have to use this equation. Then what is your ID then? ID equal to, it is again 5 milliamps per whole square into what is your VGS? VGS is taken as 3 minus, it is 1 volt. Then VDS is given 1 volt minus V square DS, that is also 1 volt square. So then the net result is going to be 5 milliamps per whole square into the remaining whole square is what? It is 2 volt into 1 volt. It is going to be 4 whole square minus 1 whole square. The result is going to be 3 whole square. So then whole square will get cancelled. The result is going to be 15 milliamps. So ID is 15 milliamps. Okay. Yes, hope you remember the ohmic current is always less than saturation current. ID ohmic always, it can be any current. ID ohmic will be always between what? 0 milliamps to, okay, up to the saturation current. That's ohmic current. So it can be anywhere between 0 to 20. So 1 volt, okay, is making the current exactly 15 milliamps. That's the Q point of the given NMOS. Okay, the Q point is found operating in ohmic, not in saturation. So the correct answer for this problem is 15 milliamps, and hope many given the right answer. Okay, that's an easy problem, but the only twist is you have to look for the maximum VGS. When the VGS is maximum, ID can be maximum. If it is operating in saturation, you will get the saturation current of 20 milliamps, but unfortunately the device is not biased in saturation. It is biased in ohmic because VDS is less than VDS pinch off. VDS given constant voltage of 1 volt. So therefore, it is not sufficient to keep the device in saturation when VGS takes a value of 3 volts. So therefore, we have to go by the ohmic equation. So you may begin with the saturation equation, but you have to prove it. If without proving it, if you are straight away taking the answer as 20 milliamp, that's a mistake. Okay, so some students might have committed such a mistake, but remember that you always in any electronics or analog electronics problem or circuit problem, always you need a quick verification of your answer. Verification means quickly the state of operation of your device. If you do that, there is no chance of committing a silly mistake. Okay, yes. And hope majority of you have done this problem well. Okay, we'll update you with one more question soon. Okay, so thanks for watching. Do subscribe our channel and also share to your friends. Okay, wish you all the best.